So we'll continue with the class. We have given different types of geometries. For that particular geometry, you have a particular hybridization. How to get this hybridization in the geometry? Then we have a mechanism. We have to get the number of domains, or we call it as a steric number. So first of all, you have to bring the steric number or the domain. For a particular domain, there is a particular hybridization. For a particular hybridization, we have a particular geometry. Simple. Steric number, we also call it as domain. Steric number is denoted by S. Domain, we generally indicate it by D. First, identify steric number or number of domains. That is the first point. For a given domain, there is a particular hybridization. For a particular hybridization, there is a related geometry. That geometry could be either parent or derived geometry. These are the points that we have to follow now. Just write this in a shortcut manner. Then we are going to use a axe symbolism. Accordingly, I will construct a table. Today you have to learn the table. Just as I draw on the board, today itself you have to learn. And from that table we are going to construct geometries of molecules. So today and in the next class, purely we are going to work out on the examples. More number of examples, it is better for you. Okay, while you write, I'll just ask a question. Can you name a compound where you can find covalent bond, ionic bond, coordinate covalent bond together? Sodium chloride, simply ionic bond. Carbon dioxide or methane or CCl4, covalent bond. I want covalent bond, coordinate covalent bond as well as ionic bond all together in a single compound. Any example for that? Yes. Ammonium? If I simply put ammonia, it is a covalent compound. But if I add HCl to it, it will form ammonium chloride. So nitrogen with 4 valency will acquire a positive charge. HCl will ionize into H plus and Cl minus. H is going and attaching to nitrogen, and this is Cl minus. So this is coming as H plus. It is not hydrogen. From HCl, H plus and Cl minus, there was a lone pair on nitrogen. That H plus is coming, and this lone pair is taking up that hydrogen. Did you understand? These are 1 electron from nitrogen, 1 electron from nitrogen, 1 electron from hydrogen. But these two are electrons from nitrogen itself. And H plus is coming and adding on to this lone pair. So this is a covalent bond. This is a coordinate covalent bond. Between the nitrogen positive charge and the chlorine negative charge, there is a electrostatic force of attraction. This is ionic bond. 3 bonds together. One best example, ammonium chloride. Have you seen this ammonium chloride? In the lab you might have seen solid ammonium chloride. You will be using it for buffers. And also whenever you put ammonia bottle, you bring HCl bottle close to it. What do you notice? Fumes will come. Those fumes are ammonium chloride fumes. So they say never put HCl and ammonia together bottles. One should be away from the other. Whatever fumes that come, those are ammonium chloride fumes. If you are inhaling those fumes, it is like you are taking little bit of ammonium chloride through those fumes. Okay, completed this one. Steric number or domain, it is one and the same. Our first target is to find out the steric number, or you have to find out the domain. Is there any standard formula to know the hybridization from your GOC, organic chemistry? Hybridization, there is a formula. Number of sigma bonds and lone pairs, that is one. Number of sigma bonds and lone pairs, that will give you the type of hybridization. Otherwise there is a simple formula type. What is that? Steric number or domain, how do you get it? Half of valency electrons, valence electrons, plus number of monovalent atoms, minus C plus A. This is the standard formula. V represent valence electrons, M represents number of monovalent atoms. You are considering only monovalent atoms. C represent cationic charges, A represent anionic charges. It is a standard formula, but anyway we are not going to use that formula. We are going to use another technique that will give you a more complete picture of each molecule. Related to this formula, let me take CH4. How will you get the steric number for this? You work it out. Steric number, S is equal to 1 by 2. Valence electrons means of what? Of the central atom. Valence electrons of the central atom. You need not get confused. Valence electrons of the central atom. So here valence electrons of the central atom are 4. How many monovalent atoms? Hydrogen is monovalent, it will form only one bond. Suppose if there is oxygen is divalent, so I should not include that divalent. Whatever may be the number of divalent, trivalent atoms, don't include. Include only monovalent atoms. Here the number of monovalent atoms are 4. Any cationic charges? No. Any anionic charges? No. So simply S is equal to half of 8. Half of 8 is 4. Steric number is 4. Once you get the steric number 4, for steric number 2, the hybridization is sp. Previously we have given sp, sp2, sp3, sp4 and so on. Sorry, sp3d, sp3d2 and so on. sp means steric number is 2. sp2, sp3 and so on, 3, 4, 5, 6, it will increase. So what steric number did I get? 4. 4 means you go for tetrahedra. This is according to VSEPR. 4 means you should not go for square plane geometry, because at the time of VSEPR there was no possibility of square plane geometry as a parent. Derived geometry it is there, but not as a parent. Werner has discovered square plane geometry. Werner has discovered geometrical isomers cis and trans. But prior to that, nobody knew that square plane could be a parent geometry. Okay? So here I got 4. Once I get 4 blindly, you put sp3. sp3 means tetrahedra. Done. This is how you can derive steric number Once you get the steric number, corresponding hybridization and the geometry. Just one more example we'll consider, not more. We have to enter into our mainstream. Let me take CO2. Tell me the steric number. CO2, steric number, half of. Central atom is carbon. Valence electrons are 4. Monovalent atoms are 0 because both are oxygens. No cationic charges, no anionic charges. So it is half of 4. Steric number is 2. Wherever steric number is 2, hybridization has to be sp. Geometry must be linear. So this is the geometry of CO2. This is the method followed, but we are going to follow another method where in detail you will know about each and every molecule, so that you will have a good idea about any molecule given to you. Done? Okay, as an example, you do carbonato anion, CO3 2 minus. What did you get? Carbonato. Sp? You got sp2. So what did you include? Half. Carbon valence electrons are 4. How many monovalent? No. So I'm just putting it as 0. Any cationic charges? No. Any anionic charges? Whatever anionic charges are there, you have to add. Cationic charges you have to subtract. So you are adding it. Half of 6, 3. 3 means sp2. sp2 means trigonal planar. So the geometry of carbonate anion is trigonal planar. Now I am making a table. Here I will give you steric number, hybridization. For that hybridization, we are going to take any number of bond pairs, any number of lone pairs, axe symbolism, electronic geometry, molecular geometry. Examples we'll just draw, we'll work out separately. But this is a table that will give you a full idea about a steric number and its related geometries. Okay. So the first one is steric number or domains. Next column is hybridization. Next column is number of bond pairs. Number of bond pairs. Here I am indicating it with X. Next column is number of lone pairs or non-bonding pairs. Here I am using axe symbolism. This could be N, this could be M number. N number of bonding pairs, M number of non-bonding pairs. Then we have electronic geometry. and molecular geometry. These are the columns to be filled now. Let us begin with steric number 2. For steric number 2, hybridization is sp. Number of bond pairs, I am taking it as 2. Number of lone pairs, I am taking it as 0. 2 bond pairs, no lone pair. So what will be the axe symbolism? 2 X are present, 2 bonding pairs are present. How many non-bonding pairs? 0. So I am writing this as A X2. E0. I need not write, but E0. Electronic geometry is linear. Molecular geometry will also be linear. It will be same. Next, for steric number 2, sp, this will not change. For one particular steric number, same geometry. But here if I take a lone pair, then one bond pair, one lone pair, the symbolism will be AX1 E1. Geometry will be linear. This should also be linear. For convenience, what I will do is I will draw geometry here. A X lone pair. A X. In the electronic geometry, don't draw lone pair. This is for steric number 2. Now I am going for steric number 3. For steric number 3, hybridization is always sp2. I should get steric number 3. All the 3 could be bond pairs, then no lone pair. Then the symbolism is A X3 E0. Electronic geometry as well as molecular geometry will be trigonal planar. You should be little fast so that every time I will be scrolling it. Then I am taking the same steric number 3. Same hybridization will not change for that particular steric number, but this I am changing. Instead of 3 0, I am taking it as 2 1. With 2 1, we have AX2 E1. So here I am putting the geometry AX2 E1. I am directly putting a lone pair. E means non-bonding pair, so I am putting a lone pair. The geometry is trigonal planar itself. I have to define the geometry as trigonal planar only. When we move to the molecular shape or molecular geometry, here do not indicate E. No E. Now what is the geometry? We call this as bent or angular. Some use V shape also, so just put V shape also. Suppose if I take 1 2 combination, If I take 1 2 combination, same steric number is 3 only. 3 plus 0, 2 plus 1, 1 plus 2. It is one and the same. Symbolism becomes AX1 E2. AX1 E2. It means there is only one bond pair but two lone pairs. So here I should not put any lone pair. I am directly putting it as AX. Then what is the geometry? Linear. But what is the geometry? Electronic. It is still trigonal planar. Make out the difference. Trigonal planar, equilateral triangle. Trigonal planar, not an equilateral triangle. Because there is a lone pair, it occupies more space. So these two are not equilateral triangles. This is a trigonal planar, angular or bent, linear. Steric number is same. Steric number is same, but molecular shape is changing. This is about steric number 3. We cannot put 0 and 3 because that doesn't form any bond. That is also a combination 3 0, 2 1, 1 2. Why not 0 3? If I say 0 3, 0 means no bonding pair, only non-bonding. It is purely atom, not a molecule. Then we'll move to steric number 4. Always hybridization will be sp3. For steric number 4, always go for sp3 only. sp3 means tetrahedral here. Let us start with 4 0 combo. 4 and 0. What will be the symbolism? A x4 E0. Then the geometry A x4 tetrahedra. This also remains same. A x4 tetrahedra. Electronic and molecular geometry are same. Then for same combination, let us take 3 1. 3 1 becomes A x3 E1. We have A x3 E1. Geometry is tetrahedra. In this case, I should not draw the lone pair. This becomes trigonal pyramidal. Steric number is same. Hybridization is same. Molecular shape is different. Then let us take 2 2 combination. 3 4 0, 3 1, 2 2. A x2 E2. Best example, your water molecule. Any other combination? let us take 1-3 combination A x1 E3. There is only one bonding pair, the remaining are 3 lone pairs. So here I draw only AX, the geometry will be linear. In this case it is tetrahedral. Is it possible to have 3 lone pairs and 1 bond pair? Is it possible? It is possible when we go to a series called as HClO4 perchloric acid, or we take the anion ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. This will be like ClO, and Cl will have 3 lone pairs. This is ClO minus. So for each of this we have an example. We have to do it separately. This is for steric number 4. Steric number 4 completed. 4 0 3 1 2 2 1 3. Then we'll move for steric number 5. Steric number 5, what is the hybridization? sp3d. We are taking 5 plus 0 combination. This is very, very important. Many questions appear from steric number 5. 5 0 AX5 E0. This is a separate geometry we have to discuss. Trigonal bipyramidal, I am abbreviating it as TBP. It is a normal abbreviation, common name, just like you have in IUPAC common name, IUPAC name. As acetic acid, trivial name, common name. But what is acetic acid IUPAC name? Fast. Suddenly if I ask some basic questions, it will take some time. Acetic acid is ethanoic acid. Likewise, I have named it as TBP, means you should understand trigonal bipyramidal. But according to IUPAC, I should write it as TBPY-5. This is IUPAC abbreviation. Even IUPAC has given abbreviations for geometries. You have to abbreviate it as TBPY in capitals, hyphen, without any space, 5, coordination number. And all this TBPY should be italics. You should not write it straight. Don't write it like this. This should be like italics. This is IUPAC abbreviation. So both are TBP, but commonly we are using TBP, trigonal bipyramidal. That is 5-0 combination. Then let us choose 5041. AX4 E1. Where should I put the lone pair? Where should I put the lone pair? Now this is a topic of discussion separately. I said it is a separate discussion, TBP. But always remember, lone pair means a localized pair. It will occupy more space. It wants more space. If I put a lone pair here, 90 degree, 90 degree, 90 degree, repulsions will be more. If I put the same lone pair here, it will be like 120 degree separation, space will be more. So any lone pair that is given should be, first of all, put at equatorial position. You first put it at equatorial position. In the equatorial position, just for convenience, I am putting it here. one lone pair. The remaining are bond pairs. X geometry is still TBP because there is a lone pair. But when you draw the molecular shape or the molecular geometry, don't draw the lone pair. What is the shape? Seesaw. This is called as seesaw. Many times asked question. Seesaw. There is one more name. It is called as disphenoidal or distorted tetrahedral. Three different names. Most common is seesaw. But disphenoidal is another name. Distorted tetrahedra is also another name. It doesn't look close to tetrahedra, but it is given in the literature as distorted tetrahedra. One clear point you have to notice here. One clear point is this is not the perfect geometry. Whatever we are drawing is not a perfect geometry. Okay? Have you drawn it, everyone? First of all, you have completed it? First you complete it, I'll tell you. There is a lone pair. Okay? Lone pair will occupy more space. It always wants more space. So what does it do with the bond pair? Will it ask it to remain there? No, it will push it. It will push it. These repulsions will occur. This will be pushed. This will be pushed. It will also push these two. So these two come close. So originally this is what I am thinking. Generally we draw this one. But if particularly bond angle is asked, this is A, this is X, this is X, this is X, this is X. Now you can see this is not exactly 120 degree. That will be lesser than 120 degree. This and this is not 90 degree. It will be lesser than 90 degree because there is a lone pair. This is exact geometry of seesaw. Bond angles will also change. There are a few exams, IIT mains, in IIT exams, they even ask the bond angles. Generally student what they think, simply they put a lone pair, remove the lone pair, this is 90 degree, this is 120 degree, it is wrong. Lone pair will occupy more space, it will push all the bond pairs. So this will not be 120 lesser than 120. This will not be 90 lesser than 90. This is the exact geometry that you have to draw. Okay? Not this one, remember. This is 4-1. Now let us take 3-2. Let me take 3-2 combination. A, X3, E2. Where should I put the two lone pairs? In the equatorial position only. Any number of lone pairs, first you start putting in equatorial position. This is still TBP. But when I come to molecular geometry, don't put the lone pairs. Show only the bond pairs. What is the shape? Most important example is ClF3. That was asked for symmetry also. What is the symmetry point group of ClF3 C2V? How many symmetry elements? 4 symmetry elements. What is the shape of the molecule? T shape. (50) TBP, 4-1 seesaw, 3-2 T shape. We can also go for 2-3 combination. If I take 2-3, then this will become AX2E3. Where should I put the 3 lone pairs? Equatorial position. 1, 2, 3. This is E and E. And in the molecular shape, don't indicate any lone pair, just put the bond pairs. So what is the geometry? Linear. It is linear. This is a potential area for questions. Steric number 5. Can we take 1,4 combination, 1 bonding pair and 4 lone pairs? E? Okay, here we have to mention X, right? Just make a correction. This is not E, this is X. Please mention it as X. E, we are referring it to lone pairs. So mention it as X. Next, can we go for 1,4? 1 bond pair, 4 lone pairs? No, we will stop it here itself. The reason is, if I take 1,4, then how many lone pairs are there? 4 lone pairs are there. Can you name an atom that has 4 lone pairs and 1 electron for bond pair? No. When I go to chlorine, how many valence electrons are there? 7. Out of those 7, if 1 is participating in bonding, the remaining 6 are 3 lone pairs, non-bonding. But if I want to go for 1,4 combination, 4 lone pairs I have to put, 1 bond pair I have to put, it means 9 electrons should be present. Do you have 9 electrons in main group? No. Transition groups are not included in VSCPR, because when VSCPR was started, it was intended for main group elements only, not for transition group compounds. Why not for transition group compounds, we'll explain later after the examples. But this is only for main group. For main group, you can't have more than 7 or 8 electrons. So don't go for 1,4. Even if you go for 1,4, what will be the shape? Hypothetically, some questions will come. It will be linear. Okay? If you go for that, it will be linear. Right, so this combination is done. Next, steric number 6. Can you complete for steric number 6? Steric number 6. Which one we have taken? Steric number 6. sp3d2 hybridization. Let me take 6,0 combination. Then this will become AX6E0. Geometry is octahedra. Molecular geometry is also the same. Octahedra. Now let me take 5-1 combination. 5-1 will become AX5E1. What is the geometry? Square pyramid. This is a derived geometry, not a parent geometry. Parent geometry is octahedra. Parent geometry is TBP. From TBP you have disphenoidal or seesaw. From TBP you have T-shape. From TBP you brought linear. From octahedra you are getting square pyramid, but directly square pyramid geometry has no importance in VSEPR in the parent geometries. This is 5-1. 4-2. 4-2 combination. AX4 E2 combination. Where should I put the lone pairs? That should have maximum separation, so that repulsions will be least. Maximum separation means one if I put above, one you put below. Both are like anti to one another. Then these are X. Here I don't put any lone pairs. Directly I am indicating the bond pairs. Now this is square plane geometry, derived geometry. It is not a parental geometry. Square plane is derived from octahedra. What are the bond angles here? Two bond angles, what are they? 90 and 180. No. No, 120. 90 and 180. No. Square pyramid 90 and 180. But is it exactly square pyramid? There is a lone pair. Lone pair will occupy more space. These four bonds which you are drawing it like a plane, it is not actually a plane. These four bonds will bend. So whatever geometry I am drawing, it is normal geometry. If you want to draw the perfect geometry, how should you draw? A, this is X, 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 X. This is A. It means the plane will not be like this, it will be like this. All the four basal bonds are now bent towards up. So it is not 90, lesser than 90. It is not 180, lesser than 180. Because there is a lone pair, it is occupying more space. This is the exact geometry. But in general you see the last one that I have drawn. In deep, this is the perfect geometry. Okay. Square plane anyway, above and below there is a lone pair, so it will be like a perfectly plane. So now you have 90 degree and 180 degree. 90 between any adjacent and opposite is 180 degree. This is 4-2. Can you take 3-3 combination? Can I take 3-3 combination? No. Reason? Because if I take 3-3 combination, 3 lone pairs, 3 into 2, already 6 electrons. 3 bond pairs means 3 electrons. 9 electrons it will become. 9 electrons is not possible. But if at all there is a geometry, then hypothetically, if at all there is a geometry, then usually we will take it one lone pair above, one lone pair below, one lone pair anywhere in the equatorial position. You have facial and meridional. This is generally taken as meridional, not as a facial one, because in facial repulsions will be more. Meridional repulsions will be less. This will come in your coordination chemistry, don't bother. This could be the possible geometry. So there is no description for this geometry because it is not possible. So don't write any geometry also. Simply if you want to write meridional. But meridional will not be applied here. So it is this is octahedra itself, but meridional type of geometry. This is hypothetical only. You don't expect it in textbooks. mention it hypothetical. It is not present, just we have written it. Next steric number 7. Let me take 7 bond pairs, 0 lone pairs, A x7 E0. Then the geometry will be PBP, pentagonal bipyramidal. PBP refers to pentagonal bipyramidal. Let me take 6-1 combination. In 6-1 we have A, x6 and E1. So any one of them I am converting it into a lone pair. What do you call this geometry? This is pentagonal bipyramidal. Above and below there is a pyramid. But here above there is a pyramid, below there is nothing. There is a lone pair, I should not draw. So it will be pentagonal monopyramidal. Pentagonal monopyramidal. And one last combination, I will take phi 2. You can check that the hybridization is not changing for any of these combinations. A x5 E2, one lone pair above, one lone pair below. This is pentagonal planar. Electronic geometry becomes PBP. This is pentagonal planar. So up till this point we have few geometries that we have to discuss. Examples. Just take 2 minutes or 3 minutes of time, go through the table once. Now itself we'll revise the various combinations of steric numbers. You should be in a position to answer. If I ask you 60, immediately you should answer 514. In TBP, if I put one lone pair, imagine green is a lone pair. Okay, what is the electronic geometry? TBP. Molecular geometry, it means lone pair, you have to discard. Molecular geometry is a seesaw. This is called as a disphenodal or seesaw. This is a lone pair which occupy more space. It will push these bonds. So these bonds will be like this. They will be bent. These two will also come close. These two will come close. These two will also come close. So bond angle will not be 180 lesser than 180. Bond angle will not be 120 lesser than 120. This is one lone pair. Lone pair always occupy equatorial position. Okay. Suppose if I put a second lone pair, it will not go to axial. More space is present in the equatorial position. Okay. If I remove these two, the shape that you are getting is T shape, CLF3. This geometry is trigonal bipyramidal. If I don't consider these two, it is like a T shape. Okay. If I put one more lone pair, that lone pair will come in the equatorial position. So 3 lone pairs in the equatorial position. If you don't consider them for molecular shape, it is linear. Okay, this is about TBP. Then we have octahedral geometry. This is octahedral geometry. From everywhere it is like symmetrical. The distance from here to here is same. But on paper when you draw, these distance look very short. Sorry, this distance look very short, this distance look long on paper. But truly speaking, it is same distance. Okay. When I put a lone pair, anywhere you can put a lone pair. This is one lone pair. If I don't take that lone pair, the geometry is a square pyramid. The next lone pair, suppose if I take cis to it, then repulsions will be very high. That will be unstable structure. Therefore, it will not come here. It will come at trans position. So now if I don't consider these two, the geometry that you have is square plane. Okay. Suppose if we have 3 lone pairs, which is not a possibility for main group elements, but just for suppose. Then it has to take up this type of structure. This is called as meridional type of structure, where there are T shapes, 2 T shapes which are perpendicular to one another. Can you identify a T shape of white? If that is say bond pair, can you identify a T shape of green? That will be like a lone pair. Both are perpendicular to one another. This will be the shape. And if I forget about this, it is just like a T shape. But it is not like a T. T is already CLF3. Therefore, I have given it as distorted trigonal planar. That is what I have given. It is only hypothetical. Okay. It is octahedra. Suppose if I put 2 lone pairs only, I don't consider this, then this become square plane. Okay. PBP I don't have the model. The model, another magnetic model is there that I'll show later. So this is the different geometries that we have studied, out of which TBP is the most important one. With regard to TBP, have you noted down these points? write a point. TBP is generally drawn as elongated structure. TBP is generally drawn as elongated structure. Generally drawn as elongated structure, while PBP pentagonal bipyramidal is drawn as compressed structure. Next, in TBP geometry, according to Bend's rule, BNTS, according to Bend's rule, the more electronegative atom, according to Bend's rule, the more electronegative atom will choose that hybrid orbital. The more electronegative atom will choose that hybrid orbital which has less s character. And less electronegative atom or more electropositive atom, less electronegative atom or more electropositive atom will choose that hybrid orbital which has more s character. Okay, that is Bend's rule. In simple words, more electronegative atom, more electronegative atom chooses axial position, less electronegative atom chooses equatorial position. Okay, so this is about VSEPR theory and some of their predictions. In the next class we are going to work out purely examples. So just to go through what are the different types of compounds, main group compounds that you have. What is the valency? Suppose if I take hydrogen or any halogens, what is the valency? Monovalent. You call them as monovalent, they will form a single bond. Oxygen, it can form double bond, so you call it as a divalent. Nitrogen, trivalent. So you just go through such examples so that in the next class it will be easier for us. And also go through the table. Go through all 7 different geometries and their combinations.